All right, welcome everybody to lesson 7 of the BioVCN R series. If you define this lesson, if you haven't already, it's gonna be in the BVCN R RStudio Cloud page. Open that, copy it, transfer it over to your workspace, and you should be good to follow along. Today's lesson is so you guys have worked with R scripts before, but this is an R Markdown notebook. And they're really easy to make. You just get the file, new file, R Markdown, or actually R Notebook. And it works just like R normally does with a couple exceptions. One, there's this little header up here, which gives a nice title and my name and some other stuff. HTML Notebook tells R basically what kind of thing it is. And the way that this works is that if I just type, it assumes it's text, so I can type some regular text. But there's also these sections where there's code. So the way that this works is much like your R script. You can run code one line at a time. So if I go here and I hit Control Enter, it'll run the code down. Okay, so it's back here where we have a HTML notebook. We've got these little things here that are called code chunks. So you've got it basically written with 3 little ticks in R, and there's some code, and then 3 little ticks at the bottom. You can make a new code chunk. You go up here, do File, Code, Insert Chunk, or Control Alt I, and that'll make a new one where you can put code in. So the way that this works is, so we put 1 + 1. We can run that as a line. Just hit Control Enter, it will run 2, or you can hit this, or you can do Control Shift Enter, and that'll run everything in the chunk. So we have 1 + 1 and 1 + 2. 2. We run the whole thing, and it'll run both this line and that line, and it'll return your results down here. And the nice thing about this is that it's saved those results, so I can always come back and see what kind of analysis what kind of analysis I had, even if I don't want to rerun all of my code. So I like this because I can just I can just work through these and look at stuff that's there. The other neat thing about these is that they make pretty output. Uh-oh, went back too far. It's in 7. And that it actually produces a HTML file, which you can send to your collaborators and they can look at in their browser, and it often looks a little bit cleaner. So I'm just going to open this notebook file here, open in web browser. So it ends up cranking out. You've probably seen stuff like this when you've looked at other sorts of R things online. A lot of stuff is written in R Markdown. So there's my title up there, the author name, and then here's my different code chunks. So the 1 + 1, I didn't save it, so it didn't come up, but if I did, it would. And then so here's this bit. And then down here, I've got some code, and this is the output of the code, which is a figure. Any questions about R Markdown? So actually, let's just keep it in this web browser, which is the thing that I printed out. If we need to modify some code, we can jump back. So basically, the first thing that I did in the first code chunk, I load my different libraries. So tidyverse, plotly, and cowplot are the libraries that we're going to be working with today. And I'm going to bring in a data set. And we're going to use the Star Wars data set because that's one that Sarah had us using last week. And to start off with, we're just going to do some basic plots of the Star Wars data set. So let's start by looking at the relationship. So in Star Wars, and actually, I'm going to jump back if I can get around the sharing thing here. Keep in mind, remember that when you load a data set, you can almost always find it in your global environment. So I'm just going to clean this up. And oh, by the way, so this is the button that runs the chunk. This button runs everything above it. So if you deleted everything, I want to run everything above it. I just hit this button there. So now we load in Star Wars. And Star Wars comes up here over in your global environment. If you click on it enough times, it'll come up. And you can see the different variables that are present in the Star Wars data set. And we're going to today, since they're nice, convenient, continuous variables, we're going to look at height and mass. So each character has a height measured presumably in centimeters and a mass, which is presumably in kilograms. Maybe, yeah, probably kilograms. Save that. And so there's a lot of statistics we can apply to continuous variables. And so let's just graph. One of the things I like to do before I even get into statistics is just plot things out. So I sort of have an idea of what I'm walking into. So here I'm going to take the Star Wars data and I'm going to pass it using the pipe. So we've worked with tidyverse before, right? So this is our pipe. It takes Star Wars and puts it as the first variable for ggplot. The first variable ggplot takes as a data set. It's going to take that in. We're going to tell it that x is height, y is mass. And I'm going to put a couple extra variables in here. I'm going to call a variable name, and spec species. And these aren't really plotting variables, but you'll see why those are useful in just a second here. And we're going to pass that to GM point. We're going to use theme cowplot. Now, if I were to just run this, so I'm going to comment this line out here. So this is my plot. If I just run this, nothing, you get nothing, right? That's because we saved the plot to the plot. If we just run hm plot, that gets us our plot. What I'm going to do is I'm going to actually pass hm-plot to this other function called ggplotly. And ggplotly is based on this other program called Plotly, which is sort of a way of interactively working with graphs. And this gets us a Plotly plot, which looks a lot like a regular ggplot, but it has a couple extra fun features. My favorite of which is that now you can mouse over points, and it tells you about them. So if I mouse over this point, it says, oh, the height is on 70, mass is 77, the name is Wedge Antilles, and the species is human. So you can get all of the data that I have up in this aesthetic variable, I can now look up by mousing over the points. One thing you'll also notice is that we have a really heavy character. And so if you mouse over that you can see that this anomalously massive character, not particularly tall, but particularly massive is Jabba the Hutt, which if you've watched Star Wars isn't super surprising. So go ahead and try, if anybody has this up, go ahead and mouse over. Tell me who the shortest character is in this data set.
Yoda.
Right. And is Yoda also the least massive, or is that, let's see, mass is 15, Yoda is 17. So he's actually more massive than, but you're right, Yoda's the shortest. And his species is Yoda's species. Okay, so this is kind of convenient. The other things you can do with ggplotly is you can do stuff like zoom in, right? So you're like, oh, what's this trick doing? You can look at them, pan, you can move around. So they're nice and interactive, and you hit the home button, everything goes back to normal, so you can unscrew it up. So let's say we want to look for correlations in our data. One thing we might want to do is just say, well, so Jabba the Hutt is like clearly really anomalous in at least the Star Wars plot. So we'll say let's look at correlations of the characters who are not Jabba the Hutt. So we'll just remove him, and we could do that with filter. And so I'm just going to use, I could do filter the name equals Jabba and his full name, whatever that is, but I'm just going to say use string detect, say find anything with the word Jabba in it and throw that out. That's only him. And then now we can look at our data without Jabba the Hutt, and you can see there's this general upward trend, right, where the taller people are more massive and the shorter, well, people in other species are massive, and the smaller sentient organisms are less massive. And then one thing we can also do is we can plot histograms over different data. So here I'm going to, because I want to use, I want to take advantage of sort of the facet grid thing. I'm going to use the pivot logger feature that we were talking about earlier in a couple lessons ago. And that's just going to we're going to do that to put mass and height on top of each other. So it's some long format data. So our names to measurement, values to value, which is a necessary thing that I pass it all to ggplot. So I say X is the value, and the panel, which I use with facet wrap, or a stereotype with facet grid, behaves the same as measurement. And then I'm going to use a histogram, and then we can see, okay, here's our data. In general, people tend to be around 180 with some high and low values, and the mass is also sort of this not quite normal distribution, but like normal-ish enough that we can probably get around away with stats. So then we can ask, okay, so now that we have our two data, we can say our height and width correlated. And I like to use the core.test function. And core test will basically just test for whether the things are correlated and give us a score and a value. So I'm going to do a Pearson correlation. You can basically tell the method is Pearson or Spearman. So Pearson is a parametric one that makes some assumptions of the data. Core test is a non-parametric thing which doesn't assume the data are normally distributed. It's sort of more of a rank-based correlation. And then you can look down here at their output. And so a couple important things with this. So one is, so for Pearson correlations, one of the most important things coming out is the score. So this is basically our R value. And in this case, it's about 7.76. And with the Spearman correlation, it's about 0.78. So very similar the row is the name of the R value for Spearman's. And then what else can we see about it? So we can also say that this is the confidence interval for the statistic, which is to say that kind of 90. So here's the thing. I'm not a statistician, and often I say things wrong. But I sort of think of this as saying that the true correlation value is somewhere between 0.62 and 0.85. Or at least I'm 95% confident of that. And then here's our p-value, which is the sort of the probability that if all of the assumptions of our model are true, that our score is actually not different from 0. And so we can say that the alternative hypothesis, the true correlation is not equal to 0, is likely to be true. It's a very small value. And we do the same thing with the Spearman. The p-value is larger, but still very small, and we still have a pretty strong correlation. Any questions about correlations or plotting or Plotly or anything? All right, I'll push on.
I can ask a leading question.
Please.
In line 39, when you were detecting the string for Java, you used an exclamation point.
Yeah.
Can you explain that? That's important.
Yeah, that is important. 35. There's nothing on line 39.
Oh, maybe because you added some text. I'm looking at the original.
Let's see. Well, I can find it.
It's right below Java.
It's right here.
Picture.
Yeah. Okay. Yeah. So, what would happen if we? Well, let's actually just look at the output, right? So if we run this whole thing, we have all of our characters and all their data, but not Java the Hutt. If I take out the exclamation point, what happens? We have just Java the Hutt. So what does the exclamation point mean? Anybody?
Like not Java
means not.
the Hutt?
Yep, exactly. So if we're to say 1 equals 1 is true, if we were to put an exclamation point before that, it's false. So 1 basically just switches true for false and false for true. And that's what's happening there. So we're saying anytime somebody does not have the string Java the Hutt, then use that one. Cool. Thanks for bringing that up. Anything else? All right, let's get into regressions. So correlation tells you the two things are related to each other. Regression does much of similar things, but the sort of the framing of it is that we're trying to say, is one variable sort of predictable from another variable? That's often the way I think of regressions. Usually if your correlation is really strong, if you have two variables, the regression will be very strong. It's hard to do correlations between more than two things. But in this case, we'll just start with doing a simple linear regression of mass and height. So in this model here, we're going to do a linear model, and you can call linear model with LM. And we're saying the Y variable, the thing that we're trying to predict, is mass, and we're trying to predict it from height. And our data is Star Wars. And so we run the model, and it saves back to model. And the best way to look at model results usually is with the summary function. So I say, well, give me a summary of that model. And then we're down here, we can sort of look at the information that's present in it. And so things that I like to look at in these models. So one is we have this little, well, so the call up here just reminds us what model it was. The coefficients tend to be pretty important. So the intercept is the y-intercept. So we say that our y-intercept, which is to say when height is 0, we expect mass to be negative 32, which really means kind of nothing, but it is important for the slope of the line. And then we have our height coefficient is 0.62. So it's positive, so it's just a positive relationship between mass and the other and height. And then we have p-values for our two coefficients. And this is the standard error of each thing. So we say that in general, we think this is between 0.62 and something higher and something lower. So what these coefficients mean is that we can predict mass with a linear equation, including the intercept and height. And that equation is essentially going to be, so we've got 0.32 here and 0.062 there. This is going to be to say that mass equals negative 0.32 plus 0.62 times height. That makes sense? But we're not 100% sure about these terms. There's some variability in there, which is why I say there's a standard error. The p-value that's good for the coefficient means that this coefficient is statistically significantly related to mass. but also that the intercept is statistically significantly different from 0. These residuals tell you if we have that plot. In general, our values are going to be a little bit off the mark, and we say on average, the median point, the point that's sort of the middles is pretty close to our guess, but these are the third quartile, fourth quartile of how far things are away from that. So some things are high, some things are low. Our worst guess on the high end is something is 57 larger, and our worst guess on the low end is something that's about 40 less. We've got all this stuff down here. One thing I like to look at is the degrees of freedom. So the degrees of freedom are the number of things that we are looking at, so the number of variables. So we actually, in this case, have 58 different characters. And then we end up paying, or sort of taking away 2 degrees of freedom, one for the intercept and one for the height. So as our model becomes more complicated, we lose more and more degrees of freedom. If we had a model that had, say, 58 different things in it, it would necessarily be able to hit every character, but it would also be considered to be overly flexible. So we want to have, ideally, we want to have simpler models that fit all the characters, and degrees of freedom are sort of a way of thinking about that. And we also have an R-squared value for the whole model, which is about 0.7, which, if you think about it, is going to be very similar to these. Let's see, if we 0.76 squared. 6. They're pretty similar to that R-squared that the regression gives us. Remarkably similar. And then there's a p-value for the overall model as well. So one thing I'd like to do once I have a model is take a look at the residuals of the model. And it's usually the fastest way of sort of looking at how well plots are working is you can just plot the model, the model itself. And so then you end up getting something, you get a series of plots that are useful for sort of diagnosing whether your model seems to have worked. So this one here, these are our fitted values. So I think these are our different masses of the different characters. And then for each mass, the model does its best to fit it. And then we have basically the amount that we're wrong, right? So this character number is 76, and if this is basically the 76th person this isn't maybe the best way of showing which characters are the problem, but this one is much higher than we would guess from our model. This one down here is much lower than we would guess from our model. Things that are right on the line are basically guessed, or on the dotted line are exactly spot on. So these guys over here are really well predicted by the model. There's other ways of doing it. You can instead do the residuals versus the rank of how good they are. You say, okay, here's ones that are bad, and here's ones that are good. Rank wise, this is called a QQ plot. Here you can take the square root of the residuals. Go ahead.
What is a residual?
So the residual is, so we have our, okay, so let's go back. We have our model. Our model is, if we take, let's say, okay, so let's actually do a specific example. Let's say we have a character that weighs, that's 15 or 50 centimeters high, right? We take 15 centimeters and we stuff it into our equation, right? So it's going to be -32 plus 0.62 times the height. So let's just do that, -32. Actually, let's be more specific. Let's do a real character. So let's go up to our to Star Wars. Let's pick Luke Skywalker. So Luke Skywalker is 172 centimeters and he weighs 77 mass units. So if we take 172 and we put it into our equation, so where is our equation? -32 plus 0.62 times 172. This is not Excel. R predicts that Luke Skywalker should be 138 kilograms, but Luke Skywalker actually weighs 177 kilograms, right? So we say, well, what's the difference between the two? And we'd say that it's going to be residual, I believe it's going to be the prediction. So 138 divided by, or minus 77. Oh, sorry, vice versa. 77 minus 138. We say we guessed 61 too low for Luke Skywalker. Or sorry, Luke Skywalker is 61 kilograms less than we would expect from our model. And so the residual for Luke Skywalker is -61. And so we can do the same thing for each character. Say, okay, so these characters are actually bigger than our model would predict by, say, 60 units. These ones are smaller than our thing would predict by 60 units. And clearly I screwed this up somehow because nobody's -61. But that's the general idea. That follow?
Yes, thank you.
And
Cool.
I think another point is you generally want the residuals, like how they are in this plot, you want them to be varying around 0. So if they're not distributed in that way, there's something probably wrong with the way you sampled or something.
Right.
Right.
So you want your residuals to be very around 0. And basically what you're looking for, right, so if they're all high, like obviously something really weird happened with your model. What often happens is you'll have one point that's really screwing up everything. So what you look for often is you go over here to this leverage plot. So leverage is a sort of a metric of like how much does each point contribute to the model itself. So is there some point that's really making things, that's really driving a lot of the model? And in this case, like these points that have a lot of leverage are actually pretty well fit by the model, so they don't seem to be screwing it up that much. And these ones that are way off the mark, like 76 up here, isn't really moving the model around that much. We can put Jabba the Hutt back in, and we can see what that does. So let's actually do that. So we'll go. Where did I take him out? Over here, right? So let's just skip this. So just Star Wars 1 is now Star Wars. There's Jabba the Hutt's now back in our graph. We can redo our residuals with Jabba the Hutt. Why isn't he showing up? There we go. So now we've got Jabba the Hutt way off here. We can do our correlations. Our Pearson correlation is terrible. Our Spearman is fine because Jabba's humongous, but like right in the middle. And then we can redo our model. So our model did look like this. Now with Jabba the Hutt in it, it looks like that. Nothing statistically significant anymore. And then we can do our residuals. And, oh, come on. There's Jabba the Hutt now. And so you see Jabba the Hutt's like, really, really not well fit by our model. But then like in general, the leverage of Jabba the Hutt isn't that much. And that's just because if you look at where Jabba the Hutt falls, Jabba the Hutt's kind of right in the middle of things. So basically Jabba the Hutt is this point that like you can't fit with a linear model, but you also, if you can imagine, let's say Jabba the Hutt was not just tall, but was also like, if you weighed, or if it wasn't just heavy, also like was really tall, you can imagine it would change the slope. It might steepen the slope of the relationship a lot relative to what you'd have from the other variables. So in that sense, that would be a very influential point. In this particular case, Jabba the Hutt is right in the middle. So like the linear model is still going to kind of try to fit everything, but maybe just be a little bit high. And then nothing is going to fit particularly well. So we say, okay, our model doesn't do a very good job of fitting anything because it's trying really hard to fit Jabba the Hutt. So that's why often removing outliers can be useful. But then when I write the paper about Star Wars characters, I need to be very explicit that like I removed the Jabba the Hutt point because it was really different, and like I have a reason for doing that. And if you have a problem with it, you can do it yourself a different way. I think that's almost. The other thing is that sometimes so these coefficients are useful. Sometimes you want to pass your coefficients to some other sort of thing. Where you're like doing lots and lots of analyses, and this output is difficult to say pass into another program. So I like to use the Broom package, the library Broom. Broom has this function called tidy, and it gives me a nice little matrix of the coefficients, right? So I've got my estimates, my standard error, my p-value, and so forth. And I promised I'd wrap up in half an hour, but I have one more thing I want to show you. So once you have a linear model, you can use the linear model to predict what it thinks, as we did by hand for Luke Skywalker. You can use it to predict the size of each character. So, and then you can use that prediction to plot out the line of prediction that you would expect to have. So what I'm going to do here So basically what I'm going for here is I've got all my points, and then this line here is the linear model's prediction of the relationship between height and mass, right? So here's all the characters, here's the predicted value. The way I get this line is a little bit convoluted. I make a data frame or a tibble with all of the possible heights. So I go all of the heights between the minimum height and the maximum height. Just stick that as one variable. You have a data frame with one variable in it called pred pre-df, just like that. And then I predict the mass using this prediction function, and then I stick that into I stick that and the height together into a data frame, and then I plot the data with GM point, but then I also use GM path feeding at that extra data frame that I made to give me that line of best fit between everything. And that is the end of lesson 7. I will take any questions if anybody has them.
Hi, Jacob. I have a question.
Yes.
I'm just haven't worked with linear models very much at all. So I'm wondering what kind of like ecological questions would you use something like this for, or like, yeah, what's the broader scope in which I would use this?
It's for all sorts of stuff. Okay, so ecological questions. One could imagine. I mean, I'll punt. Let's say instead of looking at Star Wars characters, you're looking at elephants, and you want to know if there's a relationship between the mass and the height at the shoulder of elephants. You could do that, right? Or an ecological question. I mean, so that would be but you can do that for. I mean, all sorts of things have relationships that you want to look at, right? So you could be looking at. Okay, so realistically, I did one where I was looking at damage to trees, and I want to see whether. Okay, I'm still in elephants mode. So when I was an undergrad, I was looking at whether elephants damaged trees that were on steep slopes and on rocky soil. And so I had a measurement of how steep the slope was, and I had a measurement of how rocky the soil was, and I plugged both of those into my linear model. And I had some other measurement of how much damage to the trees there were. And I said, oh, look, the damage to the trees appears to be a function of the steepness of the slope and the rockiness of the soil in that case. And it was positively related to both of those things. But then I could also do something like, is it related to some other factor? And then maybe that would turn out not to be statistically significant. So, and then once you have that kind of relationship, you can do all sorts of stuff with it. Like, I mean, you could say places where I don't actually have a measurement of something complicated. Let's say, so, I was at a seminar this morning where they're looking at the relationship between nutrients and chlorophyll. And they said that, we've measured, it's hard to measure nutrients, but it's easy to measure chlorophyll. We can go around a bunch of places measuring chlorophyll concentrations in the water, and we can measure the nutrient concentration in the water. But now we want to know what the nutrient concentration is all over the world. And we don't have nutrient concentrations, but we do have satellites. And the satellites tell us how much chlorophyll is in the water. And so we could use our relationship between chlorophyll and nutrients from some observed stuff and try to extrapolate what nutrient concentrations are everywhere. There's lots of caveats, and the linear models become much more nuanced and complicated than the one that I was showing you today. But they're a very powerful tool that I use all the time for everything.
Thanks.
I can keep spitting off examples. I mean, I just have to start going to like, what studies have I done in my life? The one I did most recently was looking at microbiome data and their relationship to whether a vaccine worked or not. And so I had a measurement of sort of how well a vaccine was working, and I had sort of a measurement of we haven't talked about ordination yet. We'll get into that later. We had sort of a value that represented what kind of microbial community it was. And I said, okay, well, the microbial community is one kind of community. The vaccine tends to work better. When people have a different kind of microbial community, it tends to work worse. And I can, one, test whether it's actually, whether it's a statistically real effect. And then two, I can say, what is that relationship?
Right. And then when you want to extrapolate, I guess your linear model has to be accurate enough in the first place?
You're right. So there's always the caveat that your predictions from the linear model are only good as the linear model is, and your predictions, your predictions are not. I mean, they sort of assume that the space you're predicting into is like the space where you did your model, right? So we could go back to like the chlorophyll nutrients one. Let's say we measure chlorophyll nutrients all over the Chesapeake Bay, and we have some nice relationship between the two of them. And now we go and we say, okay, well the chlorophyll value in the middle of the Pacific Ocean is very low, so the nutrients must be such and such based on our data in the Chesapeake Bay. Well, that probably isn't going to work because the relationship may be different in different places. But yes, you can use, and people do use linear models to predict things all the time.
And then what would tell you like that your linear model is accurate enough, or like what is the? So
you can tell whether a linear model is doing a good job of fitting the data, right? And often, and to do that with the Star Wars stuff, we look at the p-values.
Right.
And we can say like, oh, the p-values for all the coefficients are pretty high, so and it seems like it's doing a pretty good job. Whether it's good for the data that you're not looking at is a harder question, which you can argue with reviewers and your co-authors about.
Thanks.
I should point out that when your model gives a prediction, if you're using those predictions, you don't want to take the predicted value as gospel. There's some uncertainty in there, right? So we have a confidence interval for our data, and that basically says how well our model fits our data and how confident are we that sort of the mean or our best guess that the data within the data set we're looking at is something. So there's what's called the confidence interval for the data. Wider than that is the prediction interval, which is to say if there's a new point that wasn't part of our original data frame, but it behaved like the other data, how much uncertainty do we have in that prediction? And prediction intervals are its own lesson, but they're also a thing. But yeah, again, I'm not a statistician. I'm just a person who uses statistics for my own research a lot. And so odds are I probably told you something that's a little bit wrong. And so if you're a statistician and you're on the internet trolling through things to critique, feel free to leave a message about how we could, about any of this in the comments. But don't tear me apart.
I want to add one more thing about the linear models is that you can start to extend them to multiple linear models, right? So like Jacob derived the equation of his model, y equals mx plus b, but you can start adding more variables to that equation if you've measured more variables. So maybe you have a z and a w and whatever, and so that starts to become really powerful for modeling like ecological responses to multiple variables.
Yeah, absolutely. Yeah. Do people want an example of that? We could just do that. Okay. So let's look at the Star Wars. So here's the thing. So next week we're going to talk about categorical variables. So right now we're just doing continuous variables. The Star Wars isn't a great data set for continuous variables, but share screen. So here we are back in Star Wars. Birth year is also one, but we could imagine, there's a lot of missing data for birth year. Oof. Well, let's do it anyway. We can imagine making a linear model. So right now we're doing mass versus height, but let's do, I won't even do this in the notebook itself. I'll just do this in the console. So we got mass versus height. Let's instead do mass versus height plus, how do you spell birth year? Birth underscore year. Okay, so there's our model, summary, mod 1. And there you can see that you're saying, oh, look, height does a great job. We can add mass, and there's a positive relationship. Like older characters tend to be more massive, sort of, but like also the p-value is really low, which is to say that it is likely that if there was no relationship between birth year and the thing we're looking at, about 50% of the time you would get a score that is at least, or an estimate that's at least this big. Which is to say that it is likely that this estimate here is due to just sort of random chance as opposed to anything actually real. But we do have, and you can imagine if this wasn't terrible, we could have a multi-component model where we say, oh, look, we can do an even better job of predicting the characters from their height and their birth year. Just in this particular case, we can't, because that isn't a particularly good choice of variable. But there might be other variables that do a nice job of predicting that. We'll look more at multivariate models next week.